Okay, we're happy to welcome our own Sophie Libkind talking about computation in continuous dynamics.
Yay! I am excited to tell you about my favorite mystery. Okay, so here's my mystery. My computer, I think of as being composed of like zeros and ones, so very like discrete in nature. But then if I zoom in, what do I see? I see just like electrons continuously flowing through a wire. Seems mysterious. Okay, another example, you can see like fish with this very discrete like stripy pattern. But again, if I zoom in, what do I see? Well, that's just been produced by these like continuous changes in protein concentrations that like inhibit and activate each other. So again, we have this like discrete phenomena, but underneath it's actually just like a continuous system. Another one, like when I think, this is a terrible pen. When I think about things like cats and dogs, and like 2 + 2 is 4. But again, if I zoom in, what is down there, what's producing that sort of phenomena? It's my brain. And what is my brain? My brain is like these continuous activations of neurons. And the third sort of new example to me is like Theseus's ship. Seems like a thing, like a discrete idea, one concept. But then if I zoom in, there's this mysterious, thing where it's just sort of composed of these atoms or other parts where like I can sort of like swap one out and the high level thing doesn't change. So these are all examples of this phenomena where you have this high level discrete phenomena that's being implemented by some low-level continuous phenomena, continuous system. And so this feels like a mystery to me. Like how? How is it that these things, how is it that we get to think about cats and dogs even though our neurons are doing these like continuous activations? So I have some sort of desiderata for like things I want an account of this mystery to satisfy. So what is my desiderata? I want it to be dynamically consistent, which means that when things at a high level seem to change, that should sort of match how like the low level changes happen. They should be like sort of in sync with each other. Another thing I want it to be is robust. So these high-level systems don't depend on the like specificness of these low-level systems. So for example, my brain, like bonk, oh my gosh, it's a different brain, but like I can still have thought about cat throughout that process. So I want it to be robust to changes because these systems are like open to like parameters in the world. And then also because I sort of think of this as like scientists. Like in the way I have like exact parameters for Newton's equations, I actually don't ever expect to have like an exact parameterization of the brain. I want sort of the discrete level of phenomena to, arise out of something that's not so precise. So I need it to be robust. And the next thing I want it to be is also emergent. Like these phenomena all feel sort of very natural to me. They sort of come out of these systems, we humans observe them. It's not like some, alien came down and is like, well, if you do these really crazy moves, then you get a computer. It's like very attuned to the underlying dynamics of these low-level systems. I want these to be emergent. Cool. So I am now today going to attempt to give you an account of this mystery that satisfies these things. So today's account. What I'm going to do now is I'm going to draw you the picture of the account. And then most of the talk will be going through it. So the first thing I want to talk about is what we mean sort of by low-level continuous system. And for us, that's going to be a parameterized flow, which I'll call phi. And again, this is, I don't know, I often like to see sort of, this is like, I'm going to give you a spreadsheet. You're going to be like, what? All these numbers. And then over time, we'll be like, oh, that column's for that, that row's for that. OK, so just enjoy this as like art for now, perhaps. So this is my low-level system. And then I care about this functor from what I call the approximate paths of lambda to completely distributive lattices, which I will call at phi. And what this row here is supposed to do is give me all the affordances of my low-level system. Well, my low-level system and all of its affordances. So how does it want to be used, sort of, low-level sys. OK, that's going to be number one. The second thing I want to talk, oh no, I've done the wrong colors. Pretend this is purple. Cool. Purple is now green. Anyway, my high-level system is going to be a functor from a category C into poset. And we'll talk about why this should represent really a high-level, not just system, but a high-level computation, not just functional behavior, but like how is it being done. And then the last thing we'll talk about is I'm going to have a functor here called U and a natural embedding M, and this is going to be my implementation. And we'll try to talk about why that makes sense. OK, so I had an idea for this talk. The idea is once in a while I pause, and someone has to give a summary of what I've said so far. I don't know if that will work, but let's try it. And it will be a different person each time. David?
You have this mystery where high-level discrete phenomena seem to be implemented by low-level continuous phenomena, and you're giving an account of that in terms of category theory, where you will use the things in that square there.
Cool.
Where the top row is the discrete stuff and the bottom row is the continuous stuff.
Yeah. Nice.
May I suggest another mystery?
Sure.
Movies and pixels on the TV
Yeah,
screen,
totally.
and it goes higher up, over on top of the discrete things, to get back to the
Continuous things again. Yeah, yeah. Cool. All right. So let's start with our number one. It can now not be, Kevin, we could now like erase that for the online folk. OK, so affordances of the low-level system. So first, let's talk about what is even a low-level system. And we're going to start with something that I'm a flow on a state space X. So my flow I'm going to call phi naught. And that's really an R action on the state space X. And the way to think about it is I give you a state in X, and I give you a time t, and I'll tell you like, well, what's going to happen to that state if I just watch my system flow for t time. And I often think of this as coming from a vector field on X. So let's draw an example. So here is my state space X. I'm going to have these sort of special points, -1, 0, and 1. And if I'm below -1, I'm going to flow towards it. If I'm between here, I'm going to flow that way, then that way, then that way. So if I am a state, if I start out with my state here and I flow for t seconds, I might flow this way and end up somewhere like there. Cool. Another way of thinking about this same flow is as a landscape. So I can imagine a landscape like this. And the flow sort of tells us what a ball rolling through this landscape will be. So if I'm over here, I'm going to flow downwards. Then I'm going to get sort of stuck in this valley here, which is where that -1 is. So this is what we'll call a flow. And now I want to talk about sort of what are the, so this is my low-level system. What are its affordances? What are some nice like emergent things that are also robust? OK, so those things are attractors. And the slogan that I have, or that I don't know, that David and I or something have for attractors is it's a place where if you jump, you'll eventually come back. And so now what we're going to do for the next couple of minutes is try to make sense of this. So let's start with this word eventually. So what do we mean by eventually? For a neighborhood, let's say a subset of X, sort of what's going to happen to that neighborhood eventually as the system flows. So omega of n with respect to these dynamics phi naught is going to be, I'll write down something and then explain it. For all the t bigger than 0, I'm going to run my system from t to infinity, starting at those points in n, and take the closure. So the idea for me here is that I'm going to imagine
You didn't want the intersection?
oh shoot, yeah, sorry, intersection, thank you. Intersection. So the way I think about this is like, I'm going to start with this neighborhood n, and I'm going to start with like all the points here. And what I'm going to do is I'm going to imagine that after t time, they're going to start leaving a trail. So I like let my system run, and then at t time, they start to leave a trail. And I'm going to look at all the ink marks and also all the places those ink marks are approaching. And then I'm going to do that for each time and see like, these points are the places where, I can sort of close my eyes or like not have the ink marks run. But then when I open my eyes and the ink marks start to run, I'll see them approaching those points. So in this picture, yes, phi naught, thank you. Yes. So in this picture, the eventual set of this n is sort of just like this basin, because I like let them run, and then at t time they're all like here, and it just sort of starts contracting into this little valley here. And I'm also going to perhaps name this, just to change notation, ev n phi naught, to sort of be like the eventual set, so we have that in our minds. Cool. Okay, so we've got eventually. Now we're going to get what we mean sort of by jump. And this might be sort of, I don't know, this was like, yes, I forgot that this was what this means. But so I'm going to say n is a neighborhood of A. I'm thinking of both of these as subsets of X if A is contained in the interior of n. And the reason this is related to jump to me is like n is sort of saying like, how far can I jump? It's like the region, here's me and my place, and n is like where I'm going to jump and then hopefully come back to if I'm an attractor. Cool. And so, yeah, Brendan.
I'm a little confused by the type of phi naught. Like up there it says like, so that looks like phi naught is one sort of path or something. Like it's a.
You wrote that, but you did action. Your little.
Oh, yeah.
Action.
Yeah,
Right.
sorry.
I did. Okay. Perfect. Thank you.
Yeah. Cool. Okay. So now we're ready to put our whole sentence together. So def. So a subset of our state space is an attractor if there exists a compact set of subset of state space. Oh, a compact neighborhood, so a little region around A, such that A is equal to the eventual set of n. So the reason this aligns with this is you're like, okay, A is a place where if you jump, i.e. if you move into n, then eventually you'll come back to A. And so that's why it sort of aligns with this definition. And notice that because n is a neighborhood of A, we have that here that the eventual set of n is contained in the interior of n. And we call such things attracting neighborhoods. So n is an attracting neighborhood if this is true. Cool. Yeah, and a little more terminology. We're going to refer to at phi naught as the attractors, of phi naught, and a neighborhood will be the attracting neighborhoods of phi naught. Yeah.
How come the attracting neighborhoods were compact? Just because otherwise that's too far to jump?
I think so. Yeah, like you don't want to like jump far away. You just want to like a little jump, something like that.
Sorry, what is the difference between just the attractors of phi naught and the attractor neighborhoods? Like,
Yeah.
What qualifies? Because I thought a neighborhood is just a subset of the space that contains a setting in its interior.
Let me say it and then, so the relationship is sort of, an attractor is something where there exists an attracting neighborhood that like contracts to it. So an attracting neighborhood has the feature that the eventual set is contained in its interior.
Okay.
And then these are the attractors, like the eventual sets. Where you get to is the attractor.
Okay.
Cool. Yeah.
Maybe that picture would.
Yeah, let's do an example, is what is suggested? Awesome. Okay, so, right, so we sort of, I don't know, from our earlier thing about n and the eventualness, so this valley is an attractor, because if I start in the valley and I like jump a little bit away, I'm going to roll back into it. So like 1 is an attractor. -1 for the same reason, also an attractor. But there are actually more attractors. So if I look at the union of those two things, the same thing is true, right? If I'm in either one and then I jump a little, I'm going to come back to 1. So -1, 1 is an attractor. And actually also this whole interval is an attractor. Because if I'm anywhere on this interval and I get like jangled out, I'm going to come back into the interval. And sort of trivially, the empty set is also an attractor. So we don't just have a set of attractors, we actually have a lattice of attractors. Cool. Now is the time for a summary, if anyone wants to try. I don't know if this is a good idea, but let's keep trying it. Does someone want to summarize what happened here? Yeah. How about before?
Okay, great. Input being slow, but for the interval,
Yep.
why is the interval equal to the eventual?
It's not obvious. You're like, shouldn't the eventual thing just be these guys? Yeah, so, but if we look carefully, track the definition, you're like, okay, but what about that guy, Sophie? And I'm like, okay, well, how about that guy really, really close to the edge, but not actually there? That will like, it's like,
Okay.
it will take, you're like, I can find infinite points that will take you as long as you want to get there. Yeah. But,
Okay,
cool.
that's helpful, thank you.
Top point is not.
The top point is also in there, just stays there.
No, I'm trying
By
to see
itself.
why like the 3-point set of 2 values in a peak.
Oh,
because
so
it's
this
like
is-
an unstable equilibrium.
Right, because this one, if I just look at that one, if I jump, oh, I see, that one, and that one. That's a great question.
Why can't you jump just a little bit and then you will have the time to...
I think actually the eventual set of like a little neighborhood around here includes all of this stuff. Because it's like, for any time I can like wait long and find something where I have to wait long enough to come down. Yeah. Cool.
Try and summarize.
Owen.
Also, yeah,
Oh, yeah.
maybe this is what you were meaning, but yeah, there's this interior condition
Right.
that would throw that off. Because
Yeah.
the interior of the,
There's a compact set containing just a peak, but not a compact.
Not,
neighborhood.
yep.
Yeah.
It's all carefully finagled. Okay. Yeah. Anyone want to summarize? One sentence? Kevin, you look ready to go.
We're looking at the low-level systems, which have continuous dynamics, which are some flow and some space, which is at least topological, maybe probably a manifold. And we're looking at attractors, which are places where if jump a little bit away from them, eventually they'll be back.
Awesome. Okay, and they're like emergent. Like they have this like discreteness, right? But it wasn't like I had to like impose it. It like came from the system itself. So I claim I get to do this. Okay. Next up, what about, let's work backwards, what about robustness? So I claim attractors are also robust. Okay. Attractors are robust. So what do I mean by that? I mean, like, let's take that picture I just drew. So I have this, very good flow on a system. And now, like, what if I, like, jangle it a little bit? And now I have, like, this. Whoa. Okay, well, like, it still is pretty much the same. I have two attractors. It feels like that one is that one, and that one is that one. And maybe I jangle it a little bit more, and like, oh my gosh, then one of them disappeared, and now it just looks like that. So how can we, like, track this attractor, like, from here to here, and then even ask the question, like, is this one more like that one, or is that one more like that one? So this is how we're sort of trying to now track attractors as the dynamics actually change. So now we don't just want a single continuous flow. Now I want a parameterized flow. So we have a parameterized flow, which is phi, which is in our action on this thing. So, oh, that's not what I want. Just a map, sorry. So the idea is for every time, and every lambda is my parameter space, I get an endomorphism of X that should satisfy the nice group action principles. Cool. So that's a parameterized flow, and personally, I like to think about this as coming from a parameterized vector field. So I take a lambda and an X, and then I get a direction in which to travel. Okay, so let's take a look at an example of this. So the way I'm going to tend to draw this is on my x-axis, I'm going to put my parameter, and on my y-axis, I'm going to put my state space. And then for each parameter, I'm going to draw just one of our ordinary flows. So for this parameter, I'm going to put this flow that we had. So you have to imagine like it going horizontal. So now I have these two attractors, and it goes something like this. And then I like jangle my system a little bit. Now I'm at a parameter over here.
I don't know who first said
Does anyone want to continue the Okay, so here I have the same thing I have, but they're a little bit sort of like different in shape, maybe. And then way over here, I just like have a single attractor. And I want this to be continuous on lambda, so I'm going to fill in the rest of my picture. I'm going to say, let me draw it and then talk about it. So here is my system, where now you can say, okay, Sophie, like at this parameter, what are the dynamics? And I'm like, oh, there's two attractors and this like repeller mediating them. What about over here? Oh, it looks like this. What about over here? Oh, it looks like this. So now I have this parameterized flow. Cool. This is going to be a very important picture, so any questions about it?
So you imagine you're controlling lambda and then a little ball of fish.
Yeah, I get to like, I put my ball somewhere, and then I have like a dot knob that like moves lambda around, and then my ball's going to shoot around. And we're going to try and understand what might happen. I'm going to erase this board.
Lambda has no time dynamics.
Correct. There's no dynamics on lambda yet.
Lambda has some sort of topology.
These are all topological spaces. Yep.
I don't know if it's too much of an aside, but I'm trying to think what the system looks like at the interesting points. Is this?
Oh yeah, not too much.
heavy or-
They look like this, where you have, it's like a half stable point where it goes like this. So it's like attracting on one side, but then repelling on the other.
Right, so it's like an inflection point. In the
Yeah, exactly. There it's like something like that, where it's flat right here. Yep.
we made a sort of choice of hiring.
Yeah, that is a great question for David.
I prefer it that way just because I thought we wanted a monotone. Like that's a monotone.
That's a bit more than just.
Yeah, if you flow for 5 seconds and then 3 more, and you keep lambda the same throughout, then it's the same as flowing for 8 seconds.
Okay, thanks.
Cool. So we had this question about like how do we track this attractor? And so in this picture, what it looks like is like, well, I have this attractor, and then over here, it's like here, and like somehow it sort of continues throughout all those parameters. And so what our next step is we're going to define a sheaf where the sections are these like attractors that continue. So that's what we're going to do for the next couple of minutes. So first, we're going to define a pre-sheaf, which I'm going to call at phi prime on the open sets of lambda. And what it's going to do is it's going to take an open region in my parameter space and map to the set of compact sets in X such that for all lambda in that parameter region, N is an attracting neighborhood for phi at those dynamics. So modulo some relation, which I'll tell you about after I tell you about this part. So if I think about an N here, N, you're like, N is an attracting neighborhood here. Cool, it attracts here, then here, yep. Oh no, here it's not an attracting neighborhood because the eventual set lives on the boundary of N. That's the kind of thing you would get where you're like, oh no, N is not in that set. Okay, now let me tell you about the condition. I want to say that two neighborhoods are U equivalent if for all lambda in that region, their eventual sets are equal. So some neighborhood, there can be many neighborhoods, right? Like if I shift this a little, oh, it's still like an attracting neighborhood for that attractor. Cool. Okay. So then we're going to let at phi on the open regions of lambda be the sheafification. And now we can say a section is an attractor that continues over U. All right, now does this definition actually correspond with the thing where I was like, yeah, attractors that continue? Let's check that. Check that our language worked. So there's a proposition that says if we look at the stocks of the attractors of phi, for a particular parameter, those are exactly the attractors of those dynamics. And the proof uses the following fact. Uses that. Let's see, for n, a compact n and x, if I look at all the parameters such that n is an attracting neighborhood for it, this is open. in lambda. And this sort of gets to the robustness piece, because it says that like if I have a lambda and a particular attractor for it, there's some like little region around it where I can continue that attractor to the dynamics around it. So this is like where I'm like, awesome, I've got robustness. Cool. Now is a good stopping point for questions and perhaps a summary.
How does like that work on the critical point where the attractor becomes like repulsive on one side? Like, can you?
So this is not an attractor, so I don't have to worry about it. I only have to worry about that guy, which I can continue. Another attractor of this dynamics is actually the whole interval. And that is actually, so if I continue it, so this whole interval is an attractor over those dynamics.
Sure.
And this way, it continues to the whole interval again. Remember that like -1, 1 idea? This way, it just continues to the point. That's actually something that's pretty interesting. Yeah.
Okay, it like collapses back to.
Yeah.
That's interesting.
Yeah.
Thanks.
Summary? No, sorry, something else?
No.
Are you sure?
How come you define it this way instead of just starting with the sheaf? Like I find the sheaf not any easier really to think about than the sheafification.
Uh,
Can you
I
describe
guess
it?
I don't know how to even to define.
The contracting neighborhoods can change as you, for different.
Well, I mean, yeah, I might have missed something here. Why can't I just say like consider the sheaf of attractors that continue over you? Just
What does it mean?
What is it? What is it? That's how I defined attractors that continue over you. You're actually, yeah.
Are you saying define it in terms of like the atoll space of?
That's actually how it's done in the literature.
Okay.
Yeah, for the most part.
Sure, yeah, I totally meant to be saying that. Okay. So there's something, yeah.
High-level summary maybe.
Cool.
We're trying to talk about the affordances of low-level systems, and low-level system is one of these flow things, these actions.
Uh-huh.
But we need to talk about the robustness. So now we have a parameterized flow, so we can talk about robustness with respect to the parameter. And then we have this nice sheaf that describes, I guess, what it means for attractors to continue over a space.
Cool.
That's something.
Nice. Before we do our next, we're almost done with the like heavy new math stuff, according to me. And we just get to have fun. This is fun too. Okay, but let's do an example. So consider, I'll redraw a diagram soon, but just to keep going over this. So consider this neighborhood, or this open set U. What are the attractors that continue over U? So one sort of obvious one is like, I can take like this fixed point and continue it. And you're like, yeah, that totally continues. So we got that thing. Jose pointed us to another one though, which is that like this guy continues to intervals on this side. So we sort of have this whole like chunk here and just fixed points on this side. So I have sort of something that looks like this. And then also I have the empty set as an attractor everywhere. So I have that. And these again, we can give this the structure of, in fact, a bounded distributive lattice as long as X is compact. So in general, I'm thinking about this as into bounded distributive lattices. Cool. All right. We got sort of this. Now we're going to talk about the domain of this functor. Maybe I should put it. Oh no, this is perfect. Okay. So I have this category which I'm calling approximate paths in lambda. Its objects are going to be the open sets of lambda. So I'm sort of thinking of it as like, where did my blue go? A little open region. And its morphisms are going to be ordered lists of open sets in lambda. So So U1, U2, UM, which have non-ND intersections. And so the way I'm picturing that is it's sort of like this caterpillar thing where I move from U1 to UM. And the way I think about this and like how I'm sort of turning my dial on my parameter is like I'm a giant human. I can't like control my parameter infinitely well. So like I just care about being like somewhere in there. And same with when I'm trying to move it. I can't like move it infinitely precisely, but I just care about sort of like traversing these UIs in order. That's sort of how I'm thinking about these approximate paths. Okay. So now we're ready to define our functor. So, one thing, I have complete distributive lattices. So I'm just going to look at, this is annoying, I don't know how to fix it quite, but I actually want to look at the phis where this is not only a bounded distributive lattice, but where I have arbitrary meets and joins. Okay, which for me often isn't a problem because my lattices are finite, but I think this is like work to be done here. Okay, so now let's define my functor at phi from the approximate paths over lambda into continuous distributive lattices. Well, on objects, it's going to take it's going to take u to the attractors that continue over u. Great. What about on morphisms? So what is it going to do to a list like this? Well, composition in this category is just list concatenation. So I can sort of just tell you, what is it going to do on like a U1 and then a U2? So I have, I start in the attractors that continue over U1. I'm trying to get to the attractors that continue over U2. I can look at their intersection. And I have restriction maps. So what happens when I restrict the attractors to their intersections? And because I have a complete distributive, because I have arbitrary meets, this function, this restriction has a left adjoint. And I'm going to take the composite. I'm going to take, oh goodness, at phi U1, U2 to be the composite of this, and then this guy.
It's like a delta sigma data migration.
Oh yeah, so it is. And so what it does is it says, starting with an attractor of U, it's going to map to the smallest attractor that continues over U2, such that when I restrict to the intersection, the restriction of this one is contained in the restriction of this one. So I can only sort of get worse when I end up in here. Yeah, it's like I go into here, I might get worse, and then I sort of continue out. That's one way, the best thing that you could do that with. Cool. I erased my picture, but that's okay. Let's do an example. How about I erase it over here? Any questions also about a path and approximate paths in that guy?
Worse means your open set gets bigger.
My attractor gets bigger.
Or attractor, yeah.
Yeah. I have less constraints over where I am. Okay. I'm going to draw the same parameterized dynamical system that I had before. Looks like this. Okay, and now I'm going to continue this sequence of regions. Suppose I start with like U1, and then I want to go to like U2, and then U3. So if I'm moving, I can like sort of do anything, and then I have to go over here, and then over here. The end. That's how I'm imagining like turning my knob. And now what happens to the attractors as I turn this knob? So what happens to the attractors is, if I look at the attractors that continue over U1, okay, well, what are they? There's sort of this guy, their union, and then the whole interval. So the top guy, the bottom guy, their union, and then the whole interval. and also, of course, the empty set. Does that picture make sense? Okay, what about at phi u2? We did it. This guy, empty set. Okay, what about at the attractors that continue over u3? Oh, that one's easy. There's just one continuing fixed point and also the empty set. And now, as I go across, to me, so let's take a look at how does the top attractor move from u1 to u2? Well, this is an attractor where when I restrict to the intersection, the top guy is indeed contained in the interval. But it's not the smallest such thing, because this one also has that property. If I restrict to the intersection, the restriction of this guy, oh, they're the same. So this maps to that one. But this one, this bottom one, this guy here, is different, because when I take it, this one maps to this. Why? Because if I look at that big attractor, when I restrict to the intersection, I get the interval, which does indeed contain that. Okay, and then the last one goes like this. And you can sort of fill in, these all have to map to the top one, empty sets map to each other. So now I can tell you what happens as I turn my dial. If I start near this, I'll end up near that. If I start near that, I'll also end up near that. And if I showed you the maps in the other order, remember these are ordered lists, I would show that this fixed point eventually becomes the top one. Whew, okay. How are we doing? I'm now done with one. So let's all take a collective breath.
Approximate path thing, did they just disappear anymore? Browser literature, just as a common
I think I mean, I couldn't find it anywhere. So, but I also agree that it seems like quite nice. Should be nice or something.
Do you have any idea whether there's a standard notion of path and a locale? Because it feels like something like this
Oh.
is sort of
No, this is like
all you could possibly do.
on the to-do list feels like, man, I wish I really understood like frames and locales and stuff. Yeah. I think another thing that this you might want, so there's this whole notion of timing which I've glossed over, which is that I actually have to move slow enough to make sure that I actually converge the attractor. So you might want this to have some notion of time so that you can make sure that you're doing that, you're going through your path at a reasonable rate or something like that. Yeah. Yeah. Cool. Right, I'm going to erase all the boards. And we're going to talk about high-level computations. So to me, it's really important that the high-level phenomena, it's not just functional, like inputs and outputs, but it's actually like, it's not just what happens, but like why it happens. Because in my computer, you can imagine that actually in my computer is like a person, and you send them information and they like spit out the answer. And that's a very different computation than like a logic gate in my computer, which is a very different computation than like a lookup table of all the answers in my computer. So we're going to follow, yikes, where are we?
Oh, they fell off already.
They got
There.
lost.
They got reordered.
They got reordered. No problem, I think. Oh, here we go. Okay, sorry. Okay, so 2, high-level computation. So following sort of like theory of computation, we're going to define an automata-like thing that's going to be our notion of high-level computation. So we're going to start with, if this is my category, and I have a functor into set, that's a discrete dynamical system. Why? Because this object is going to give me a set, which I think of as the set of states, and this morphin is going to give me an endomorphism of those states. So for example, I might have 2 states and a swap between them. Cool. All right, let's do more. I want, what about instead of, I want a system where it's not just one thing that can happen, but many things that can happen. So now I'm going to have morphisms here. a functor into set is one of these, but with input. So here, suppose this was like even, odd. And this is like if I send a 1, the parity changes. But if I see a 0, the parity doesn't change. This is like counting the parity of a sequence of 0s and 1s. Cool, okay. This is a boring category. Why not make it any category? So I call this a context-dependent discrete dynamical system, because now instead of just having one set of states, you can have different sets of states depending on the context. So this might be like, here's my C down here. This is like when my system is on, but when my system is off, I only have one state. And in the on context, I can have two inputs, 0 and 1. In the off context, I can only turn on my machine. And when I'm in the on context, I can also turn off my machine. Now I have to tell you what these two arrows do. This is going to sort of reset my machine, and this is going to forget if I was even or odd before. And then the last thing I want to do, I want to change this, is to make this into a poset. So it's a context-dependent discrete dynamical system that's also hierarchical. And the idea here is now the states aren't just a set of states, it's a states with some structure. An example might be if, like, over here in the on context, I can count modulo 4, but I also sometimes forget and just remember if I'm even or odd. This would be an example of a hierarchical context-dependent discrete dynamical system. And that is my high-level computation. Questions? The hierarchy? Yeah. It gives a hierarchy on states. So like, one thing I'm imagining is like I have states 0, 1, 2, 3, 4. Oops, 0, 1, 2, 3. And I'm sort of counting modulo 4. But sometimes I mess up and I like forget where I was. So I have also the fact that like some of them are even and some of them are odd. And then I can just do my counting up here.
I think that the state is it's never in 0 and even at the same time.
Yeah, it's just in 1. Okay, cool. I'm going to erase this. Oh, well, too late. All right, last thing, we need to talk about implementation. So what does it mean for one of these to be implemented by one of my continuous flows? So 3, implementation. So to give an implementation, I need to give a functor from my context category into approximate paths on lambda, and a natural embedding of m from S into this composite. So what is all that data? That data is, for each context, an open set. And so here's where I'm thinking about, like, if I have my continuous dynamics and I actually want to like implement this context, I'm going to just be like somewhere in there. Okay? And an embedding of the states over that context into the attractors that continue over that region. So this is sort of saying, if I had my picture up, yeah, let me draw my picture. So if like this is my UC, it's like to implement the context C, I just need to be somewhere in here. And this is saying, okay, so maybe like this attractor up here corresponds to cat, and this attractor down here corresponds to dog, and the attractor that's like the interval corresponds to like some animal, and I just don't know which one. Or some cat-dog hybrid, something. Cool. Okay, then for an input, I also need a caterpillar thing, UA, which starts out at UC and then continues to some UC prime. something like that. And again, the idea is if like on my computer I want to make this sort of discrete switch, under the hood what I'm going to do is follow a path sufficiently slowly through that approximate path. Yeah?
So does this kind of imply that you can't use any C that's not a free category?
I don't think so.
So your point is that there are no equations between morphisms
Oh,
and
I guess there are equations. Well, yeah, but
They're pretty dumb.
There's some restriction on C. Maybe it doesn't necessarily have to be free, but like it would be hard to have. You couldn't have any non-trivial inverses in C
Why not?
unless you sent them to the
Same thing. Oh yeah. Yeah. That seems like a problem. Yeah. One thing of note is that there's a whole two-categorical story for that picture, and I sort of wonder if that would help.
Okay.
But that's a great point. Yeah. There's something I don't like about this approximate path. Like it feels like it's missing stuff, and I think you're sort of like pointing at the thing that's not quite right. Yeah. Cool. Yeah. And then just to write down the last condition. So what should it satisfy? It should mean that I have my two embeddings. And if I sort of update my state, my discrete state according to SA, if I like, or if I drive my system by this, it should produce sort of the same map of attractors. That thing should commute. So this is saying that like if I want to skip from dog to like this thing up here, I can just like slowly turn my parameter up, and the attractors will do the right thing. Where I see my system will be implementing the right concept. Cool. That is the story.
Is it dynamically consistent?
Oh yeah, wait, well this is dynamical consistency. Yeah, good news. We wrote the whole thing such that I could make a third check. Yeah, I guess the other things I want to say. So dynamically consistent is like this diagram commuting. And then there's a question about like, does this language work? Like, can I use this account to like say things that I want to say? I have a project with some computational neuroscientists that sort of like tries to use this account to make sense of this story. And then also more recently, I've been thinking about like, how does it make sense of this story? And so it's cool because it works sometimes for some things. Yeah, the end.
Let's thank our speaker. Questions for Sophie? I have a question. Continuing the conversation, I think you were just kind of starting with Owen.
Yeah.
What I was thinking seems missing from these approximate paths is a notion of refinement, like a string of open sets. Like you can contain a lot of paths, and if you like shrink all of the sets, it should be the same path, maybe.
Yeah.
But you said two categorical, and that sounds double categorical. Is it really double categorical? Because you need to have a map for the little set.
Yeah, I agree. Yeah. I made the story two categorical. I agree. I was like, man, this feels double categorical. I think I tried double categorical. Something went wonky when I moved over here.
Mm-hmm. Are the small morphisms in lattices monos or something? Like, what's the double category of the lattices?
I guess I was imagining it as like a two category where they're identities. So maybe that's my problem, in that if I chose something like monos, that would actually, yeah, that sounds right.
Like in a smaller set, you have less attractors than in a bigger
You actually have
set?
more attractors, so it would be the opposite. Because we saw, like in this example, this has more attractors than things that continue over that. Yeah. You can like see more when you're in a smaller region.
So I'm just trying to connect this to things I know or at least have heard of. So like in topological data analysis, people often look at this idea, or if you have some continuous parameter and you tune it, and you can look at and see which features are stable. Are those, and here, are those ideas relevant or useful in this context with regard to your parameter space?
Yeah.
How does that fit into this story?
The place I found that relevant was, it's not mathematically tied, but just in applications, like trying to find these continuing attractors, like what does that even mean? Like the strategy that we had is sort of to do topological, right, so there's a topological data analysis story about how to find these continuing attractors in applications, where you sort of look at, what do? You look, right, so you look at like all the, you run your system forward. You start at a bunch of parameters and also a bunch of initial conditions. You run your system forward, you get like dots like this. Then you do sort of the same thing over here. And then you have this sort of zigzag pattern that you can use to track the attractors.
I have a question, like, this looks very related to, in control theory, you try to basically reach a goal state that you converge to, and you have like Lyapunov functions that tell you whether you converge to the goal state. So like, in some sense, does this allow you to do something like an algebra, or how to arrive at different potential goal states that you want to get into? Like, could you apply this, or have you seen related work in control theory where people use this to reason about the behaviors that they can?
I haven't seen it, but it sounds exactly like, you know, this language to me is like working if it can sort of say something about a problem or like connect to a problem like that. Yeah, exactly. Owen?
Following up on the double category, two category thing, I had a different idea than you, which may be similar to your idea, which is that, yeah, when you start with these open sets, you naturally get a simplicial complex, because where there's like an edge between two things, if they intersect, yeah, and then there's a triangle.
Yeah.
Right. And then, like, instead of just going to the free category on the graph, you could do like the free two category by throwing in like some sort of like a triangle morphism.
Yeah.
Whenever you have
Something that's like, I can't follow all the math in my head as we talk, but like something that's ringing true about that is that the reason I care about like this ordered list is actually so that I can make sure that like this, like capture this. Like that when you, if I want to compose like a path that's like this and a path that's like this, that I really have to go around versus just like staying there. So this is feeling like that to me.
Questions? Okay, let's thank our speaker again.